Hello, here I am again. I am Professor Anita Wasilewska of Stony Brook University, and here are my introduction to the theory of computation lecture notes, which follow the Christos Papadimitrou and Louis' book, Elements of Theory of Computation. Is absolutely excellent book, but my lecture notes contain like more detailed version of it. That's why I presented this as the lecture notes. So here are the slides. Now we are in chapter 3, which the title is Context-Free Languages. And we have 3 set of slides to cover today. Context-free grammars, pushdown automata, and context-free grammars, and languages that are not context-free. And then we will need another device which would deal with languages which are not context-free, and that would be our chapter 4. So context-free grammars. Finite automata, as we know, are formal language recognizers. They are devices that accept a given word or string from the language. Context-free grammar, a new device, they are certain type of the formal language recognizers. They are devices that produce the string. So automata recognize, and context-free grammar produce our strings of words of the alphabet. So such a device, producing a language device, begins when we have a given start symbol, and we need a start symbol to construct the string. Operations are not completely determined from the beginning, but nevertheless are limited to a finite set of rules, and the process stops, and the device outputs a completed string. So the language defined by such a device is the set of all strings that the device can produce, and now we need to write a model of such a device, and that model is called a context-free grammar. So context-free grammar, now so grammar, context-free grammar is 1, 2, 3, 4 pieces, where V is alphabet. We already know sigma, our sigma, which we use the same, which is a subset of V, is the set of terminals. So we have, and V minus sigma is non-terminals. And we have, so these are really this is the whole alphabet. In the alphabet, we have our sigma, which was our automata alphabet, and this is called terminals. And V is non-terminals, and R is finite set of rules. And what the rules do is a relation which takes non-terminal V minus sigma and returns a string of the alphabet. And S is initial symbol, or start or initial symbol. So that's where we start. So this is our definition of the grammar. And of course, when you have the grammar, we need to have we have a grammar, you need a well-established notation. So we denote non-terminals by capital letters with indices if it's, so when you see capital letter is a non-terminal, and And terminals are, like before, are letters of our not terminal alphabet, sigma if it's any element of the alpha of sigma, A, B, C's, whatever we want to have. So now the rules, as I said, so we have well-established notations. Now the rules are formally, right? A rule is the set of A, U, a tuple because it's two-argument relation, where A is non-terminal and U is in string of terminals and non-terminals. So how we write? We write the rule, instead of write a tuple, we write that A in the grammar U for the tuple A U, and normally we write a rule of the grammar would be U instead of writing here, and we want to distinguish the grammars. So we write the rules in that forms, non-terminal, capital letters non-terminal, and here's any string of our alphabet. So this is the form of writing the rules of the grammar. And of course we need to define one-step derivation. So now we have those rules, and you have a finite set of that type of rules, and we define one-step derivation. What does it mean? That in the grammar, from the word U, we derive the word V. What does it mean? That we have first, we need a rule. So it means we have a rule A. Okay, let's write it like that. We have a non-terminal, and then U is written, this word is written X, A, some Y, and V is X, V prime Y, where you have a rule which says what we do. The rule says that we replace A by V prime for certain rule in R. So it's replacement. So we have from the word, you derive from X, Y, A, Y, if there is a rule which says what? That A is replaced by another word, V prime, and that is the rule, and that's how you derive step by step. And of course, the language is, when you have one-step derivation, the language, now we have very easily, the language would be the set of words from sigma. That's why it's terminal alphabet, such you start at the initial symbol and you have reflexive transitive closure, you get V, so W you get through. That means we have a computation which starts at S and goes by the rules, and the end is W. Remember, is W must be in sigma star. So that formally, so for example, we write, you can write it as W1, W2, so this is our computation, or if in general is in the grammar, when we sit in one grammar, you write it like that. But also the computation, we will be writing in two ways. because formally the computation of is S. You have a start symbol, you derive some words, and then you derive, and then at the end you have W. So that is a computation which is a computation or generation, a computation in a grammar. It means I generated the word W, and we also can write it like this, because this is one-step computation between. So that would be a computation in grammar, or derivation in grammar, derivation in G. You can write it using the symbol for one-step derivation, or you just skip the symbol, not write all the time, and you have derivation in G of word W in sigma S, and in between you have one-step derivation. It means in between you have, what does it mean? You have rule which says how you replace, how you get from W1 to W2. For example, you have a simple grammar. Let's look at the very simple grammar, and that's how, this is a general grammar. Now let's look at the grammar where V is S, A, B, and you can see immediately that there's only one non-terminal, and you can see that sigma is AB because we decided that sigma are small letters, and you have rules. So let's say that I have one rule which says S replace A, S, B, and I have another rule which says N, S replace E. So let's look at certain derivation. For example, I start with S as always first step, and now I use rule 1, and I write A, S, B. And now I am here, and I want to use again rule 1 again. So it means you replace S, but A, S, B. So you have A, and I replace S by A, S, B, B. So this is a derivation, 2 steps of a derivation. Look, this is not in sigma star. This is a nice word in V star because it has this S inside. So in order to head, because the language of grammar is the set of W in sigma star, which you can derive. So you need to get rid of this. I call it way out. Way out. And here is my second rule, which says I have way out. It means now, the next step, I apply R2 and replace S by E. So I have A, B, B, and that is a word in sigma. So I can write that I prove that A, B, B is in the language of that grammar. And if you look at this, you can keep going. You don't. So we stop here to get A, B, B. Now you do again R1 and again, and then this is my way out. So I prove A to the power 3, B to the power 3 is in the language. By induction, you can see, you prove by mathematical induction of the length of derivation that language would be AN, BN for n greater than 0. So that is a simple context-free grammar which generated a language which, what we know about it, we know that that language is not regular. There's a new definition we say that a language is a context-free language if and only if there is a context-free grammar, that L is generated by a context-free grammar. So we just proved our first fact that language AN-BN is context-free. But we remember that that was the first language, simple language, we proved was not regular. By pumping lemma, we proved that we need there are other languages that regular. So that is not regular. So we prove that if you say that RL is the class of regular languages, CFL is class of context-free languages, we proved that we have a new class of languages. So they are not the same. So now the question is, because we show one element which is context-free, it's not regular, we'll have plenty more examples of those elements. So the next goal now is to prove that the class of regular languages is a proper subset. We know that they are different. Now we want to prove that regular languages is subset of the class of context-free languages. So, but before we prove that would be our nice theorem, we show that certain regular languages are context-free languages. It's not general proof, but for example, we prove that A star we know is regular language, that is context-free. And what is the grammar? The grammar is as simple as it can be. I want to introduce a new notation. So now we defined a grammar with sigma is only one element, because I want to have a language would be A star. This is regular language. So, and I make rules S, A, S, of course obvious, and S way out is E. And we write this when you have two rules, because they have the same left side of the rule, we can write the set of rules is S, and now I replace S by S, or that is or I replace S by E. So this is, instead of repeating, that is our notation if you have more rules with the same symbol, non-terminal symbol on the left. So that grammar would contain just two rules and sigma. And of course, you can see that the language, you have A, and then you apply AS, and then you apply AAS, and then you have A to the power S, whatever is the power, and that is exactly A star. So we prove that the language is X star, and again the proof is on the length of derivation. So, for example, that is another beautiful non-regular language. WW reverse show that is a context-free. What does it mean to prove that the language is context-free? It means you have to define the grammar. So again, now we have a beautiful grammar, and now we are speeding up. It means I have a grammar with the set of rules, which is S, and I write, I want to have WW reverse. So A, S, B, sorry, A, S, A. Now, B, S, B. So you can see that I have S, I produce A, S, and now I use that rule. So I put instead inside I replace S by B S B A, and so on. And of course you need the way out. So the next rule, the way out is E, because I want to have way out. So would be A B B A, and this is in sigma star, and that is W example of W and W reverse. And by induction you can prove, and we prove that the language would be, in general case, the language would be WW inverse. Again, you do it by induction on the length of derivation. So another simple context-free grammar. I'm just giving you those examples because they're typical examples. We will be coming back to this kind of examples when we will be talking about pushdown automatas. But also lectures have plenty more examples. So another grammar, what's happening, you have similar grammar, right? So you know that that part does WW reverse, but now you do the way out. See, now the way out I do not by E, but I put a letter C. So sigma is A, B, and C, and my juice run out. So now what's happening when you have this rule, the third rule instead, the way out is by putting C. So now you have a C here. So that would be, the language would be WC, W reverse, where W is in A, B star. So sigma now has A, B, C is our sigma, and it produces the words W reverse, where W is in when W is in A, B star. W equal reverse, W equal W reverse is another beautiful grammar, and you can check that would be, you have W equal W reverse. So you want to produce W which are the equal its own reverse. So again, you start with W reverse, but now you put on S, you put A or B or E. And you can check that, this is an example, you can check that that is, when you do the reverse of the word produced, you get the same word. And again, this you need to prove by mathematical induction over the length of derivation. And of course, when you have those two rules, they produce, and here's a, they produce, if you have SA or SB, you have the first language, this is W, that is WW reverse, but now if you put those A and B's inside, so you have WW reverse, and you put A, and you check when you put A, you would get, you would, or you put B, the whole language at the end would be W equal W reverse, and here's the proof. And with all the cases, this is a formal proof that that language is W equal W reverse. Now, we want to prove our theorem that regular languages are a proper subset of context-free languages. So we introduce a new context-free grammar, which we call regular grammar. So we say that the grammar, we put restrictions on the rules. So we say that the context-free grammar is regular or right linear. Also, we can introduce the notion of left linear. So if the rules are of that form. So what does it mean? You write those rules. Really, when you look at this definition, it means that the rules are G is right linear. You can also have left linear, or we use the word regular because if our rules are A, W, B, there are two kinds of rules only, W. You say right linear because you end on the right side of the W, you have a non-terminal, or just A replaced by W. So this is a subset of context-free. So it means at most one non-terminal on right hand side. And also, if you put the rules similarly on B, on this side, they are called left linear. But so you can see that you have left linear grammars, right linear, and whatever we prove for that, we can prove for that. So that's why we just talk about called this regular grammar, and when you have the left linear, you can do everything in similar way. So, and here's an example. And we want to prove that our goal now is to prove theorem that regular languages are proper subset of context-free languages. So, first, let's look at an example. I want regular language L equal L M. That was also our theorem, main theorem for M finite automata. So to prove that regular languages, it means that if you have language which is accepted by a finite automata, I can construct a grammar, and also vice versa, that if I have a context-free grammar, if I have regular grammar, so the language which is, we can construct a finite automata which would have the same language as the regular grammar. So let's look at an example. Here you have a nice regular grammar. For example, we have AS. You can see there's only one on the left, at most one, or you can have this. And I want to construct a finite automata which would have exactly the same language, as that regular grammar. And okay, here. So now I do an example. You have a regular grammar, which is S, A, S, A, E, and you have A, B, A, for example, A, B. And I want to construct M, finite automata, such that language is language of M. So I do non-deterministic automata. The automata has to mimic what the grammar does in inverse. Grammar creates a word and automata has to accept it. So what I do, we do delta, and you have this rule. So what does it mean? In a state of A, you read A, and you, in a state of S, you look at this rule, and you go to the state S. So you take that our M, our states of M are just the non-terminals. So here would be A in S, non-terminals. So if I have a rule which replace S by AS, in automata it would be in a state S, read A, and go to S. And now this rule would be, what does it mean? That rule S implies A would be in the state S, read nothing, go to the state A. And now, in that would be what? In a state S, you read nothing, and that was way out, right? This was a way out, so F is a final F. M has one final state, which is F. So that our way out would be F would be just a final, it's one final state. So you can see that now. So I encode it in the rules of grammar in our moves of automata. What this rule would say, that in a state A, you read A, B, and you go to the state A. And that rule would say, in a state A, you read A. And what does it mean? This is way out, way out. So you go to the final state, and the same in a state A, you read B, and you are finite state, and you, so the automata rules, the rules of the grammar generates a word, and automata would read that word exactly in inverse sort of way. So, for example, here I wrote you that here would be the derivation of the grammar would be A, S, and now the automata takes this word, and what it says in the state S, reads A, goes to the state A. Now in the state S, read A goes until gets to B, right? Until gets in a state S reads reads A, now in a state and now goes to I switch wherever, I can always switch to A. So at this moment, in the states I read A, I switch to A. And now I am in the state A, I read, because it has mimic whatever the grammar was doing, in A reads A. And so I would, in a state A, reads AB, you see here. In a state A, reads AB, because it created AB. So here, it created AB. So here it reads AB, goes to the state A, and then when I am in A, so I accepted the automata. Okay, so let's, and there's more. So here we can prove now in a similar way the theorem that language is regular if and only if there exists a regular grammar such that language is language of the grammar. And so and that would prove that the class of regular languages is a subset of class of context-free languages. So I have now to prove in general way in the other side what's happening where the language is regular. So let's say we have a regular and I want to construct the regular grammar. So when language is regular, I means I can have the deterministic finite automata. So I take regular, I go to a deterministic finite automata, and I construct from the automata, I construct a grammar. In which way? Very simple again. That was an example. Now it's a general construction. I construct, if you have a regular language, I construct the rules. I construct now a grammar, which is V sigma R S, where V is, and I have automata, deterministic automata. So I have deterministic automata, which is K. You have the same sigma. You have delta S F. So now V would be sigma union K, where sigma is terminal and K, the states of the automata, would be non-terminal, and S would be initial state of automata, and the rules would be that I am in a state Q, so now terminals are our states. I write A P if delta Q A equal P, automata, the rule, and Q E, where Q is the final state. And of course, I can change little q into capital Q, and that would be non-terminal. So the rules you can write Q, capital Q, A, P, capital P, if small q, etc. But you can leave the, or you can enumerate, you can use the capital letters for the states. So that is, and of course we show that the language, it means you have a derivation of if and only if P0, you have any derivation, P0 sigma 1 P1, so it means delta of P0 Q1 is P1, so you have that rule, so you have the proper derivation in the grammar by definition. Now, of course, the language is included in the language of grammar, because if for some p in f you have a derivation from s to p, and delta QAP is if and only if that holds, so you have the similar derivation in the grammar, so language is in the grammar, and vice versa. So the second part is, which I already show you on previous example, that given a regular grammar, I define non-deterministic automata in a similar way, right? You have a rule AWB, that was what we did as an example. That is exactly the same pattern as we did for the example. And then you have a proof that is proper. And now we can do it easier. It means drawing the diagrams. Let's look at the automata. Q, A, Q, 1, A, B, B, and you can, this is the my automata, which would be the grammar. You read the rules of the grammar would be in the state Q, Q0, right? The rules would be that in the state Q0, read A and go to the state Q1. And in the state Q0, you read B and you go to the state Q1. Now, here, when you are in the state Q1, you read A, you go to Q1, and in a state Q1, I can write it like this. You can read B and go to Q1, and also you have what's happening. This is final state, so you need to have a rule Q0 way out in the grammar, and this was a final state, so you have Q1E. So that is grammar regular, of course, you can see, and this is automata. And now you can rewrite it with the proper notation. Q0 was initial, so Q0 is initial because it was initial, so you replace Q0 by initial state, so you have a nice I am going to A, right? Q1, Q0 is initial, and Q1, let's call A. And now you can replace, use the proper notation for non-terminal, would be like that, and you rewrite this in proper, but that is a, you have your grammar and you change. Q0 was initial, so is S. Q1 was another state, so is capital A. So you have only two, and also you have A, S is E, because you had the way out of Q0, so you have a proper grammar. And now you have another example, for example, very complicated automata. Immediately from the diagram you can read, and you have So now it's nice because here's another example. Here is automata, and you can see which language it is, and immediately you can write, you can use the same symbols, and you have the rules of the grammar, and automata rules of the grammar, regular grammar. So it's useful to have. So now also we have a simple, like before, we have a lot of simple questions, which I'm not going to go through all of them, but also that I created all these questions for you to help you studying the material. Like, for example, we covered certain, up to now, we covered material about grammars, and here the set of terminals of context-free grammar is a subset of alphabet of G. True or false? A set of terminals and non-terminals of grammar form an alphabet. The set of non-terminals is always non-empty. The set, you can answer those with plenty of questions, and of course I give you answers to those questions, but when you study, please look at the questions, and on the website, course website, is hundreds of questions, and try to answer them, because that is a very good way to study the material, and then you can check if your answers are correct. So here is, and they are called true or false, and that is, for example, terminals non-empty is false because terminals was sigma. You know that sigma can be empty because sigma is a finite set. So there are a lot of very nice questions. So I just want to make you aware that you have them to study on the course website. And also some of them are just, you have to know how to construct a grammar. You say that this language is context-free, WW, yes, because you construct a grammar. So also in the lectures and in our slides for our video lectures, you have basically almost all solutions to homeworks from the book. So there's a really, and it is structured in a way also to help you to study. So now we have a new type of automata, which will be connected with context-free languages and context-free grammars, which are called push-down automatas. So here is a richer model. So you can see that we have, I already wrote it, a tape and finite control and reading head, which moves exactly as it was before, but now we have another part which is called a stack or push-down store, where we can put and remove symbols from. Here we have input word, but we can operate on the store, which we can put things in the store, remove it, and so on, so that the whole operation is much richer than in normal finite automata. And of course, automata remembers one symbol at a time, and so you can think about this push-down store as a store. It means when you read, you can remember what you've read. So automata remembers what it already read by putting one symbol at a time and the top of the stock. Always the operation is on the top of the stock. So this is like a memory. I read A, I put A on the stock. I read B, I put A on the top of the A, and so on. So that is a new Now, the symbols also can be removed from the top of the stock, and also it can be checked with what is on the tape. For example, here I read B, and I have B on the top of the stock, and I can have instruction which says if you read B, you can remove that B from the B, the same letter B, the same element of sigma from the top of the stock. So it can be check against the input. Of course, you can also have instruction that I read A with B on the top of the stock, I can remove B. So you have those, we want to have those actions of putting things in our memory, in our pushdown store. It's called pushdown store or stack, just to short. And we can put things in, we can remove, we can check the way we want. So we have this operation between what you read and what you want to store and how you want to compare them. So, and also the word is accepted because you move one, and here you have your states like normal, as we did in our finite automata. Word is accepted, it has been read, stack is empty. So our final, we accept the word if you did all those operations, and then and the stack is empty. So you build your memory, and then to accept the word, you have to have instructions which would empty the stack, and automata has to be in the final state. So here, that's a very simple example that the language here, I want to push down automata, that language is W reverse, W in sigma star. And so you can see how here I want to check if this word is W reverse. So for example, here we will have configuration. So configuration is always read. Configuration of automata is in a state what's happening, what is already read. So here I have W, and here would be W, and I want to check that this is W reverse. So so how I proceed, if you want to construct the automata, I read A, I put A on the bottom of the stack. This is empty, this does not exist. So let's, and now I read B, I put B, I read B, I put B, I read A, I put A, I read B, and now I read B here. So I'm here, and now I want to check this, I don't know, so that would be not deterministic, but now I said, okay, I am here, I want to check if what is already on the stack is, I read now this B, and I compare this B with the stack, so that I put our W on the stack, and now I check it. So I read B, and I remove it from the stack. I read A, I remove from the stack. I read B, I remove, and I read B, I remove it. I read A, and stack is empty. And I read the word, so the word was accepted. In general, that would be automata, which would accept W reverse. So now we have to put everything into nice mathematical terms and to be able to prove. So the idea is automata would read a word, putting the reverse on the stack, because you build the stack from the bottom to the top, and then you compare what's happening. So this is a nice, simple automata. So, and the goal, our goal is now to prove a theorem similar to the theorem for finite automata, establishing the equivalence of regular languages with finite automata. It means we want to prove the main theorem, which is the class of languages accepted by pushdown automata, which we have to build the model, is exactly the class of context-free languages. So we have now to define what is this pushdown automata in nice mathematical similar model, and all the operations which we're talking about in the proper language, and then to achieve this goal to prove the main theorem. And then, of course, so we know that we already did finite automata in regular languages. They were equivalent in the sense that any language accepted by finite automata is regular, and for any regular language we could construct a finite automata. And here we have context-free languages, which are languages which were generated by context-free grammars. And now we are going to define pushdown automata, which is extension, in a sense, is extension of finite automata, which would do the same for context-free languages what the finite automata did for regular languages. So, and the idea is exactly, so the idea is pretty simple, because when you want to construct a grammar, because now we need to go okay, for regular grammars and finite automata, we had this idea. We already show how to connect finite automata with the grammar. So it means the rule of the grammar AWB was transformed into a transition in the automata. So it means the rule would say read A, in A, read W, move to B. So that we want to extend this idea now to the pushdown automata. So it means if you have a rule, a nice simple context-free grammar with the rule A, B, A, we cannot do the finite automata because we don't know what to do with B. So we translate it to corresponding transition to be defined formally of PD automata, which says M in a state A reads A, puts B on the stack, that was put this B on the memory, and goes to the state B. So state reads, does something with your stack, puts B on the stack, and goes to the state B. And later, those symbols from the stack can be removed when you keep reading, and so on, and finally stack is empty. So we have, so that is the difference. This gives you regular languages and finite automata, and that information on the right side, on both sides, would you need stack to remember things. So there's pushdown automata. So here is the definition of pushdown automata. Now we have a little bit more pieces. It means now M is K states sigma delta transition as F. But things are, oh, and you have, I forgot something. You see, so I was going too fast. Never go too fast. You have a new piece, gamma. And then you have delta, you have S, and you have f. So you have a new piece of, in our definition of, and of course, so finite set of states. This is an alphabet. Sigma is input. Alphabet. And gamma is stack symbol. So you have two alphabets, input and stack symbols, and of course S is initial state, F is K, and transition. So delta is transition, and I will write here just to is K, sigma star, gamma star, times K gamma star. A little bit more complicated, but not too much. Because what I said, in the state K, read sigma, read word, and do something on the stack. So this is a stack operation. And go to another state with changing the stack, or whatever, doing something on the stack. Now, notation, stack alphabet. Alpha, beta, gamma are stack symbols. And the others are like before. And of course, it doesn't need to be a function. And now, when you look at this, so stack symbols, I will put here alpha, beta, gamma, etc. So just to distinguish, and sigma is normal, sigma A, B, sigma, etc. Right? So now, what is delta? You have state, you have word in sigma, and you have something on a stack. You see, that's why it's beta. And now you have a state and gamma. So this is element of delta. Simple. In state P, in state P, with, this is the stack information, beta on the stack, beta on the stack, P, state, read, this is beta on the top. So remember that all the operation on the stack, top, happens on the top of the stack. So P, read, with this on the top here, go to Q, replace, that is, replace beta by gamma. So you replace beta by gamma on top of the stack and go replacing, right? So you can say that in a state P, read W, that is the top of your stack, go to state Q, replacing beta by gamma on the top of the stack. So these are our movements of the automata. Now you have special operations, which which we'll be using a lot because it's nice to have it short. It means is push. A is P, U, E, Q, A, and pop A, which is P, read U, A, and you have to pop. It means in a state P, read U, empty, the top of stack is empty, so it means you replace put A, push A, it means replace put A on the top of the stack, and here you read A in a state, A is on the top of the stack, you pop A, it means you replace, you erase A from the top of the stack. And configuration is of course current state of M, W in a Q is represent the current state of M, and W is unread part of the input, and gamma is the content of the stack. And transition is between configurations. And now the transition is, of course, transition relation in automata is in a state P. Automata, this is unread part, so reads U. B is on the top of the stack, so and the instruction says replace B on the top of the stack, replaced by the gamma. So that is your transition. If and only if you go from this to that, if your instruction delta says in a state P, read U, and this is X is unread part of the stack, and the stack is beta alpha. Alpha can be empty, right? So it means the transition replace beta by gamma, and that is the content of the stack. And of course, the language is the set of W that, as we said many times, you start in initial state with W, stack is empty, and you end up in the final state, you read the whole W, and your stack is empty again. And you say that M accepts if and only if the language is in there. So we have, so it means again that M accepts W if and only if there's a computation, transitive reflexive closure that starts with W in empty stack. It starts at SWE and ends up in the final state after reading D and emptying the stuff. So that means that. And we have class of finite automata is a proper subset of pushdown automata. Pretty obvious. It means finite automata, and we take deterministic because we have choice, and we construct a pushdown automata where stack is empty. So alphabet, we said that gamma was an alphabet. Empty set is a perfectly good alphabet, so gamma is empty, and delta mimics the our automaton. It means PUE, it always is empty, so it means PUQ is in delta of our finite automaton. And then you have more useful transitions. So I want to put more useful transitions is compare and pop. It means compare and pop if compare, it means you read A is on the top of the stack, you pop A. So if A is A, you can pop A, and here is compare A with B. It means you read A, B is on the top of stack, you pop B from the top of the stack. So these are push, pop, and comparing are the basic transitions which we will be using defining automata. So, for example, here you construct W, C, W reverse. We already have a grammar. We have grammar like this. We know that's a context-free language, and we have grammar for that. We know that's a context-free language. And here's the transitions. So what transitions do when you have to read, you read them that, again, automata pushes A remaining in the state S, and pushes B, because when you read A, you put B remaining in the state S. Now, if reads the C, this is a middle, so you read like W, and if you read the W, remember when you read the W, that would, in the state S, you read the whole W, what is happening, that you put on the stack the inverse of W, because you build the stack from the bottom. So you read W, you build your stack, and now if you see this C in the middle, because that I want to compare what's left. So I switch to the final state, and now I do only comparison. All the rest is, if I see A, I compare A and pops A. If I see B, so whatever I compare exactly what is on the W, on the remaining part of the input with the stack, which was W reverse to what you read already, and that's a simple, and then there's a trace. Now, when you trace a computations, I copied it from the book, because you can have, so what you have a state, unread input, stack, and transition. So this is my word, stack is empty, and you read until you see you read, you read A, you put A, you read B, you put B on the left, so the top is from right to left. And now when you read C, you can see that what you were putting the reverse, and then when you read C, you switch to F, and now you compare, and that is the deterministic automata. It's the simplest automata. Now, what's happening when you don't have the C? The C tells you when you start to comparing, when you don't have it, you have to be able to compare at any moment. So you put another transition that you can switch to F in any place. You are in state S, you read nothing, you do nothing to this stack, you switch because, and you keep switching until you sort of find the C, this middle place, when the switch is proper, and then you would be able to remove the stack. So you have the similar automata. And here is writing all those things together. So it's important to, I will give you another way of writing it. And I explained here that the simple is the marker. If you don't have a marker, you have non-determinism, and you just do a lot of. Now you have another automata, which is, I'm not going to go in detail, which says W has the same number A and B's. you see an, bn is the same number consecutive a's followed by the same number consecutive b's. Here is a little bit more complicated because you have a word and you count a's in the whole word, which can be anywhere, with the number of b's, which can be anywhere. So that's a nice automata. It's a little bit more complicated, and there is a nice trace of computation. And also, I explain you exactly step by step what each step means and why. So, and there's a lot of examples you have to study, which are more involved than just example what they do. So now, to make everything a little bit worse worthy, the pleasure in finite automata were when we could draw the diagrams. So now we are going to draw diagrams for pushdown automatas as well. So we define a diagram of pushdown automata. Very, again, simple idea. You have state. You have state. In a state P, go to the state Q, and you write U, comma, beta, gamma. So this is reading, and this is operation on the stack, on your diagram. So what does it mean? That you have P, U, beta, U, beta on the top of the stack. You go to the state Q and replace beta by gamma on the top of the stack. So this is my delta. So in state P reads U, replaces beta by gamma, go to Q. Of course, that is our delta. So now we know what this does. And of course, what that means, if I write you this, U, E, A, Q, means push A. Read E, stack empty, and push A. And now that is the same with the loop, so we don't need to. And now we have, here we have the state P, do nothing, and push A, doing nothing. So again, W, push A, reading U, but if you write P, E, E, A, Q, reads nothing, pushes A on the stop, on the top of the stack. So it's push A, reading nothing, but this is a particular case of this one. And again, this is, so this is push, reading U, and here you have P, Q, U, A, E. It means pop A. And the same with the loop, and the same, you just reads nothing, pushes A on the top, very good delta. And now when you have such a diagram, and this, it imitates the finite. This is our finite automaton, right? In a state P, read U, go to Q. And here, in a state P, go to U, nothing, stock is empty, doing nothing on the stop because stock is empty. So that is imitation. So you have that any finite automaton is a pushdown automaton. And here you have a nice diagram. Good exercise. Write all the components, as we did with finite automata, and find the language. But you can see immediately what it does, that reads A, pushes A on the stock, and reads B, pushes B on the stock. Reads A on the stock. Reads B, B on the stock. Now, reads C, so you have A, B, and C. When reads C does nothing to the stock, it switches to the final state. And now, if reads A with A on the top of the stock, empty it, reads B with B on the top, and pop B. So you have all. The language would be WC, W reverse. Nice diagram. So now we can go. So again, what would be this diagram? Again, the right components, but you can see what's happening is the same, except that the switches non-deterministically from initial to the final at any moment. So the language will be WW reverse. It is non-deterministic. Now there's another diagram. Find components. It's good to find components, and I will be asking you to write all those components because you can train yourself to understand what is really going on. And here you have, that's what I mean, that the components are and what's happening. So you think and you write this, and the language would be A to the power A, because that is this. And then you can have a n to the power Bn. So now our goal is to talk about pushdown automata and context-free grammars. So our final goal is to prove the main theorem that they are equivalent languages, context-free languages. It means languages defined by context-free grammars is exactly the same as languages accepted by pushdown automata. That's we really achieved with that definition of automata what we wanted from the beginning. So, we have, just to remind you, we had a main theorem for finite automata which I called FA main theorem. The language is regular if and only if is accepted by a final automata. And now we want to prove a similar theorem that the class of languages accepted by pushdown automata is exactly the class of context-free languages. So context-free languages, by definition, are languages which are generated by context-free grammar. Remember, the regular languages is different definition. That's why we needed regular language was a language which was defined by regular expression. So that's why we had that finite automata main theorem. So now we break our main theorem into two pieces. It means each context language is accepted by PD automaton, and language accepted is context-free. We prove that that is really difficult, and we don't have time, and it needs a little bit more tools to develop to prove the second part. So, but it's pages 139, 42, beautiful proof in the book. We do them a while. So we want to now show that each context language is accepted by some PD automaton. It means that we want to construct. So M we construct has only two states, P and Q. That's already good. Remains in a state Q after the first move. M uses V, the set of grammar terminals. Remember, V is the set of grammar terminals and non-terminals as the stack alphabet. So our stack alphabet is terminals and non-terminals. It means you have G, which is V sigma R capital S, and M, I want to construct M, which I put K equal to states, PQ. Sigma is sigma. Gamma stack is the set V. So it means, remember, in grammar, sigma was a subset of V. So these are terminals and they are non-terminals. That is more things in V. So here, stack alphabet contains contains sigma if we want, right? And we have two states. This is initial state, and final state is only one. So this is initial, so you have only initial finite state. And delta contains three types: P, E, E, Q, S. Initial state of automata, initial state of grammar. So you see, this is initial state of automata, P, and this is initial state of grammar. And Q, E, A, Q, X, for each rule, A, X in R. So what it does, in initial, you read nothing, you put, this goes on the stack, and go to the, in the same state, and replace A by X. So that's exactly what the rule imitates the move of the rule. And 3, Q, C, C, Q, E, for any C in sigma. Because this is the emptied stack. So if you read with sigma, you empty the stack, so that would be all. And that all is in your final state. You see, so that is only, you are in initial state only putting the initial symbol of the grammar, and then you are everything what is happening, you put what grammar does on the stack and empty the stack, all in final states. So the transitions are designed so that the stack during the accepting computation mimics the leftmost regular grammar derivation of the input string, and carries out a step of such derivation on the stack between such steps and pops from the stack any terminal symbol that marks the symbol from the input. And that the process continues, exposes the leftmost non-terminal, so the process can continue until the input is read and the stack is empty. So I want to see. Yeah, sorry, I didn't put it on the blackboard, but I'm going back. You have those transitions which I put on the blackboard, and now what is that you have for each rule? Yeah, so I did it. Yeah. And then if you see E, yeah, that's good. Okay, I'm sorry, I was just... So let's do an example that you have a grammar, right? So that was our grammar W, C, W reverse. And then the rules of transition, you just retranslate it, exactly would be, that is a rule in the grammar. That is, you put this is E, and now you are already in the final state. S, the rule says S implies S, A, S, A. This is the rule, this is the rule, this is the rule. So you have the rules of the grammar, and then you just put all those rules of the grammar on this. You see, this is your you replace S on the stack, and then you keep removing improperly. And here is nice computation, which would accepting the word A, B, B, C, B, B, and you can see that, you see here, that is your initial, you go, and the rule says that you put S, and now S, you read A, S was S, you replace by AS, and so on. So you read and replace, and then you replace everything back. So now, and there's more examples. So now we have the most sort of important part. All parts are important, but it's important part. So as we did, we had, for final automata, remember we had a pumping lemma, and regular languages, we had pumping lemma, which gave us a method of proving that a language was not regular. So if you could construct automata, it's the same here. A language is context-free. Now you can construct grammar, you can construct automata, because you know that you have the choice, but it's a positive answer. Now, how to prove that a language is not context-free? And remember our first language, which we use to pumping lemma for regular languages, right? We proved we had a pumping lemma that proved A, N, B, N is not regular. And then we had the whole theorems, which were closure theorems. We have all facts about regular languages, which help us to, when you know that certain languages are not regular, how to build, how to prove other languages not regular, and so on. So basically, we want to repeat similar process now for the context-free languages. So that is the slides. So we want the PDF main theorem prove equivalency, that language is context-free if it's generated by context-free grammar and vice versa. So that enrich our understanding of context-free languages, but because provide two different methods of recognition if the language is context-free. But the problem is how to recognize that the language is not context-free. Of course, we will want to have some kind of pumping lemma for context-free languages. So now we are looking at the tools establishing context-freeness of languages. And we will prove some closure properties of the context-free languages under certain language operations, as we did in the case of pumping lemma, union of languages, concatenation, and so on. So we prove those theorems, but now we'll see which of those closure theorems would hold also for context languages or not. And also we present a pumping lemma, which is a tool of proving. It's a tool, it does not always prove. It's a tool of proving, a powerful tool of proving, if we can, that the language is not context-free. And of course, pumping lemma, together with closure theorems, as we did for finite languages, we can combine them and prove more languages not to be context-free. So now we are going to prove 3 closure theorems. As I said, they're important for proving with after pumping lemma of proving languages not to be context-free. So first of all, positive theorem. Context-free languages are closed under union, concatenation, and clean star. Now, the second closure theorem, that intersection of context-free language with regular is context-free. And 3, context-free languages are not closed under intersection and complementation. Remember, the finite, the regular languages were closed under union, concatenation, intersection, complementation. They were very regular. Now, the context-free languages are not closed under intersection and complementation. And we put it as the third because that we prove quickly, and that we need pumping lemma. We need to prove that some languages are not context-free in order to prove that context-free languages are not closed under intersection and complementation. It means that you need some examples. So first is very pleasant and easy. It means that context-free languages, what does it mean? Context-free, it means that we use the definition that context-free language is the language generated by a context-free grammar. So we have 2 context-free languages. That means we have 2 grammars. And now we want to construct closure of the union. So it means you construct the union of 2 grammars as follows. Of course, the alphabets are the union. S is the same. Remember a picture of automata. And the sigma, we assume that they are all is the union. So we defined a grammar, which is the union of 2 grammars. And so grammar is union. And the rules are, of course, the rules of the first grammar and rules of the second grammar, and then I have a new symbol S, so new S, because this one has S1 and S2, S you go to S1, and the rule S go to S2, so it means that in a grammar you can go to the first grammar or to the second, and of course the language, if you have derivation in this grammar, if and only if you have derivation, you go from S to S1, so you go here, and from S to S2, so you have the languages, the union of languages. So concatenation is also easy. It means that you have a new symbol and you concatenate. So it means you have S1 and S2, so you take S and you go to S1, S2, and then in S1 you go to S1, and S2 you go to S2, so you have concatenation of languages. Clini star is also pretty obvious. It means you have a new symbol and you have S go to S1, right? So here you have a loop, so you have S1 and S1, so you have a loop on S1, and here you need a way out because the language is you have to get rid of this S, so that for two reasons. One, that Clini star you need to have SC to make the S is for the Clini star, but also you need the way out from this S. So, and now we prove the closure theorem. The intersection of context-free language with regular language is a context-free language. So it's a little bit more sophisticated. So we already have all those tools. So context-free with regular. So let's take R for regular language and L for context-free. So now regular language, by the main theorem, R is accepted by certain, what I take, deterministic pushdown automata. And so the language R is the deterministic pushdown, deterministic finite automata. So for L, you have some pushdown automata, and for R, you take deterministic. And I want to construct the automata which would be intersection of those two automata. It means the language would be intersection of languages. And we did similar as we did for closure of finite automata. We take as the set of states of that new automata, you take the Cartesian product of those two automata. So you take K would be Cartesian product of our regular and push down. Of course, the stack would be the stack alphabet would be the stack alphabet of push down, and S would be the Cartesian product, the tuple S1, S2, and the same for F. And we define M like we did the same, that they operate on coordinates, one as the finite automata and the second as the push down automata on the coordinates. You have to do a little bit more details in order to match those coordinates, but basically it's the same idea as we did for finite automata, the direct construction of finite automata. So now we have pumping lemma to prove the closure theorem 3, but also to show how you do how you deal with with context-free languages, and we can do it. And remember the pumping lemma, it looks almost like a pumping lemma. Like pumping lemma was that the word you can split, if for regular languages, word could be split into 3 pieces, that y was non-empty, and then you could pump the the middle part as many times as you could. So now we do it a little bit more complicated. It means language is regular, language is context-free, so you have a context-free grammar. And the pumping lemma says there is a number k depending on that grammar, such that any word of the language of the legs greater than k can be rewritten as 1, 2, 3, 4, 5 pieces, where those blue pieces, v and y, here was only 1 piece. So now, more complex languages, you have to split into 5 pieces, such that v and y can be pumped any times. It means n and n is the same. So that's why it's called pumping lemma, that can be replaced by any, can be pumped any times you want. So, so this is, in this sense, is generalization of our pumping lemma. The finite languages, the proof was very nice, using pigeonhole principle. Now things are more complicated, and we're not going to prove it now, but I'll show you how to use it. So here is, and remember, for regular languages, we use the pumping lemma in all details to show that a, n, b, n was not regular. The language was not regular, and now we show that language a, n, b, n, you add 1. You see, we could handle by counting by the very easily by the pushdown automata, because we had memory to count those a's. But now, if you can count those 2, but we cannot count 3. So this is the simplest n greater equal 0, not context-free. I cannot, I'm comic attraction. Next time we will invent Turing machines, which of course they would accept those, that language and many others, but also more general grammars, which will show you that we have a general grammar which would accept that language. So that would be like end of the whole thing. So now let's look the proof. Let's take n greater equal of k, and so assume, so then an, bn, cn has a representation, our representation in 5 pieces, y, z are non-empty, and such that you can pump. And that is impossible, because for an, bn, cn equal that, and is equal this, and a, the v or y contains 2 symbols from a, b, c, because when you split this, they have one or the other has to contain two symbols. So in this, if it contains two symbols from A, B, C that split Y and Z, you get, if you pub this and you pub this 2, contains a B before an A or a C before an A, and if V and Y each contains only A's and only B's and only C's, then that cannot contain equal number B and C, end of the. This, when you look at the, it's really the same proof we did for regular languages, so AN, BN. We were looking that Y should look like this, this, and that. So this is the same idea. So that it's not, and this is contradiction. So we prove that it's not context-free. And now we can prove the closure theorem 3, that context-free languages are not close at the intersection and complementation. And first, not close at the intersection, and the second is not close at the complementation. So not close at the intersection, so it means that these languages are context-free, and we proved it in those many, many exercises for context-free languages. These are two context-free languages, and you can see that why and how to construct the grammar. These are the same and this is different, so they are context-free languages. And intersection gives exactly this language, so contradiction. So that's why we needed to prove it. We needed a pumping lemma to prove that at least one was not language was not context-free. So very similar. And context-free languages are not close at the complementations. It's again one of my favorite proofs that you assume that two context-free languages, and you take the intersection, which you write by the Morgan law as the complementation of the union, so that if they were close on the complementation, that would be context-free, that would be context-free, because if it's close on the complementation, we prove that the union of two context-free languages is context-free. If it's close on the complementation, that whole thing would be context-free language, and contradicts that the intersection is not context-free. And then you prove, as we did for regular, you use pumping lemma, born more complicated ways, that to prove that certain languages are not context-free. For example, this is not a context-free, which is like, you see, this is like almost like AN, BN, but you have this dot A to the power P prime, A and square, WWW is not context-free. That is context-free, we already proved today, and this is not context-free. That are the proofs by pumping lemma, very nice proofs. So what does it mean? That the pumping lemma, we can use pumping lemma to prove that many languages are context-free, but it doesn't mean that we can always find the proof. There are some simple context-free languages that cannot be, we know that they are context-free, but they cannot, they know that they are not context-free, that cannot be shown to be context-free by direct application of pumping lemma. So one of such languages is AMBN, where M greater than N, or M is prime and N is greater equal M. We prove not to be context-free using a very interesting theorem, which is different in structure than pumping lemma. People develop different strengthening of pumping lemma and still couldn't prove, none of them could prove that language is not context-free. And so Parikh invented the theorem, which is pretty, of course everything is complicated, but I brought it in to show that you can have a different method than pumping lemma. It's interesting because it gives another method of proving languages not to be context-free. So the Parikh theorem says that if L is context-free, then you construct something which is theta L, is semi-linear, which is certain property, where that theta L is a certain well-defined set of n tuples of natural numbers associated with L. So, of course, I am not going to go to details, but what it makes connection, you have context-free language, and you have a method, constructive, well-defined method, associated certain types of tuples of natural numbers associated with a context-free language. And then, so it means that he proved that theorem, that set of tuples have certain property also, which is quite possible and easy to prove. So it connects with certain different property than pumping lemma property of context-free languages. So hence to prove that the language is not context-free, we look at those set of tuples and we show that it's not semi-linear, so it's not context-free. So it's another very different method of proving that language is not context-free. It happened that people couldn't prove that language to be non-context-free. There were new versions of pumping lemma. I said, I cannot prove that's not context-free, and also nobody could prove that was context-free. So that is I brought that's a new nice. So also we use this Parikh theorem to show that simple that nobody also could prove other methods. Property of context-free language, that every context-free language over one symbol alphabet is irregular. So that was proved by a Parikh theorem. And also now you have plenty of exercises. So for example, WW prove that's not context-free. Hint. You see, I want to prove WW not context-free. Hint is that I know that this language is not context-free. So what do you do? As we did with regular, we know that assume that is context-free. You intersect that language, which you assume to be context-free, I want to get a contradiction, with regular language. And we have closure intersection of context-free and regular languages. And when you intersect, you get a language which is not context-free contradiction. So we did this type of proofs also already for regular languages now. So that is also somehow a power of pumping lemma or power of closure theorems, that you can, knowing certain languages to be not regular or not context-free, and the closure properties gives you power to prove that other languages are not context-free. And again, applying, we construct the PD automaton that W has the same number of A and B's. It was context-free. And we use pumping lemma to prove that, so we know You see, we know that the same number of A's and B's, but W has the same numbers of A, B's, and C's. This is context-free. If you add 1, public lemma shows that it's not context-free. And of course, AP, BN, this is also nice because that is a regular language. You see, that is a context-free language, right? The first non-regular context-free language. But if you take that P is a prime and N greater than P, you get not context-free. So, and then you have like a lot of yes/no questions. Again, that for the chapter, I always give you, for this each piece of the chapter, I give you a lot of nice yes/no short questions, and they are good. You know, I think they really provide you the good way of study. Like for example, this language is V in V S. You get the derivation of W. It's not true because you must have a sigma star. So it teaches you paying attention to small details and definitions. So there's a lot of nice, simple questions. Some of them are like constructing the grammar. The language W equal W reverse is context-free because you can construct a grammar. Here's a grammar. And the regular language is accepted by pushdown automata. Yes, because by main theorem, and the regular language is a certain finite. Accepted a finite, and any finite automata is a pushdown automata which operates on empty stock, which we already, this is always review. And so you have a lot of review questions and more. And nice exercises, and more exercises, and more exercises. So I will leave you at this moment with all those nice questions and exercises to study, because I think you so please, thank you very much. See you next time.